Welcome to our April 2024 monthly meeting. I have a background image from one of our new members, Jacob Vanderwelt, and I believe he took this picture down at CGO, but I'm not exactly sure. It could have been one of the others. I don't have the full details on it, so just give him a, hey, that's a cool thing when you see him the next time. And then we have our wonderful board that consists of me, Trina, your president. John Zemich is online. Dave Faulkner is in Chicago. And then we have Matt Dunham. Ahmed, I believe, is online as well. And Jesse's in Texas. So hello, welcome those that are joining us. And I'm so glad everyone is here. Welcome to our new members. We have I didn't count how many new members we had, but we have several new members. So thank you very much for joining our little club. The image is of the sun through Conrad's hydrogen alpha telescope taken with his cell phone. So very much for all of your all of the new members. We have officially reached 703 total members. So congratulations to our 703, or at least 700. So thank you. Thank you, everybody. Events before the next month's meeting. We have Mars, we have Saturn coming and Venus next to the moon. We have our total solar eclipse on Monday, which also is our new moon. A lot of conjunctions going on along with the Lyrid meteor shower. So hopefully you guys will be able to get out and get a good view of that. You know, just go outside, lay down on the grass, look up, there you go. And then we are back here on May 2nd for our monthly meeting. And that will go back to being in person and on Zoom. Tonight, there just wasn't anyone that was attending in person, so we're just doing it all online. So thank you for participating. We're still working on the Better Know a constellation, but Ranch submitted our member minutia, and we would like to have a couple of people volunteer to do just a quick little presentation about anything that would interest them. Claire's kind of taken the top lead on that one, but it doesn't have to be as detailed as Claire's. Just anything that's of interest to you, that you want to share some information about, 10, 15 minutes. That's all we ask, and I would love to have you to come up and share with us in person or online, whatever you're more comfortable with. So just let me know if you are able to do that and help us out for the next couple of months. And of course, this is Alan's view of the sun with a sunspot on there. So I thought that was pretty cool. The Loner Scope program, I'm sure Anton's not on, but for those that are new, we do have within our club with the membership, you are able to take out a telescope and keep it for a month, and Anton shows you how to use it, and then you take it everywhere, wherever you want, do some projects. I think we have 18 or 19 loner scopes available, and you can get those on our website, along with the great courses, DVDs, and books that come with that. They're very interesting courses, and don't worry so much about the year, but it's really interesting, and I've watched several of them, so they're very, very cool. And just a lot of fun. So take those out of the library too. So that's helpful and interesting. And to do that, you go onto the mnastro.org website, and go under membership, and you'll see the Loaner Scope program link. And then you will just fill in your name and information that you're a member, and pick which top 3 items that you want to take out for a loan. And Anton, I'm going to get in touch with you as soon as he has one available. And that is it. And then you just give it back at the pre-assigned time. So pretty easy. If you have any questions, let us know at the info, or even in sending it to Anton's. Well, if Anton has his own email, but info@M&Astro will get you there too. Upcoming star parties, we have ELO, which has started their star party schedule. So we have April 13th and April 27th at 7 o'clock at Baylor Regional Park, available for public star party and for volunteers to come out and help with that, and key holders especially. So hopefully if you're a key holder, you'll be able to go out and volunteer for that. The BSIG observing session, Suresh, do you want to take a couple of minutes and talk about that?
Sure. So we're excited. We get to finally go back outside after not a bad winter, but a winter nonetheless. So we're aiming for Saturday, April 27th, starting up around 7 p.m. at Metcalf Field. Hopefully by then, if we're lucky, the second electric outlet will be functioning by then. So thank you, board, for approving that, and John and whoever I'm forgetting, Clayton and the rest of the guys that are working on that. Thanks for taking care of that for us. But we may actually have 2 outlets going again back at Metcalf. And so we're already looking for volunteers for that session. So if you can help out that night, that'd be awesome. And we've already had some inquiries about that. So I think some people are excited to get out and get their scopes checked, for fixes and the like, and get out under hopefully a clear, dark sky. So that's it. Any other questions, just let me know. Thanks, Trina.
Yep, perfect. Thank you, Suresh. I appreciate that. So along with that, we have the JJC, which is open for key holders, CGO, which is open for members. Everything should be working, is available for, the pads are cleared, the snow is pretty much gone. LLCC has their first observing weekend, April 12th through 14th. So those that are going to be back in town, great. I won't be able to get up there until next time, but check the forums for that. And you do have to sign up for that, I think, at least to reserve on the forums a room in Markham House, and that way they know they have a room, have it open and waiting for you when you go up there and observe on the field. And these are some of the key holder trainings. April 27th for ELO, JJC is in May, CGO is April 20th. I forgot to take off the tentative, but we do have that date set. And LLCC is always during Northern Night Starfest. There's a couple of days that are training with videos and hands-on working of the 2 telescopes to get them out of the building and set up so you can use. And that is August 27th through September 2nd. And I believe registration is open as well for Northern Night Starfest. And that information, I think, should be either in the happenings along with on the forum. If not, you can always send an email to LLCC's committee, and they will provide you with a link to sign up for that. Yep, there's all of them. Apparently I forgot to hide that one, but that's okay. And okay. Astronomical League Awards, we have, I think I'll just kind of scooch through this one. But it is a place, as the MAS is part of the Astronomical League Awards. They are our parent organization, and they provide us with observing lists and other challenges to help with our interest in our astronomy obsession. And just kind of giving you a focus as to go through. If you're not sure exactly where to start, there's a place to start there. Constellation Hunter and just Sky Pups if you're for the younger kids to go through that. The Astronomical League also provides us with the Reflector magazine that you will receive as a new member or as a member of the MAS. And that's just a little list of some of the over 80 observing programs options that are there, and they've sorted them down by difficulty on their website. So if you want the beginner one, intermediate, advanced, and what kind of tools that you need and what kind of observing styles that are required. And that in the middle is or on the left is the Messier pen, along with a couple of the certificates that you receive. So hopefully this will inspire you to get out there. And I know one of them also has something to do with the solar eclipse. So take a peek at that and see what could help you out and keep your interest going. There are no awards right now, but we're hoping that next month we will have some. And hopefully next month, Jerry will be able to actually do this part of the presentation. So that will be wonderful because he is our astronomical lead coordinator. He's been out doing some other things for the last couple of years, so we've been taking over and holding his space. The MAS is on YouTube, so every presentation is recorded and put online at our YouTube location that's shown there. But otherwise, if you want to go to YouTube and just search for Minnesota Astronomical Society, you will find our monthly meetings, the beginner special interest group videos, some parts of the winter BSIG programs are recorded, so that's put up there. Yeah, there's a few other things that are going on there as well, so take a look and sign up. The Gemini articles, I believe, just published for April. That should be coming out shortly. And it's all written by members. So if you have something going on, say the solar eclipse trip, please write an article for Father Brown. He loves having those articles come in. And I don't think there's any other club that does just member only articles. So they're interesting to read and wonderful to write. And I encourage you to.
Trina?
Yeah.
This is Father Brown.
Oh, hi.
I am looking for articles for Gemini about the eclipse. So if anybody is going or has gone already, I'm really looking for them to describe their experience going and coming, whether they have a clear sky or clouded out. So please write a short article for Gemini for the June issue and beyond. Thank you.
Thank you. Appreciate that. Thanks for being on tonight. But yes, it's, even if you get clouded out for the eclipse, there's always a story that goes along with it. The challenges of getting there, the decisions that made you change your mind or continue on to enjoy it just through, the cloud layers. So everything is very, very much needed, and we want to hear your stories. So thank you. And if you have anything that's happening out there that you want to let everybody else know about, send an email to the secretary at mnastro.org, and we will put it in the happenings, which comes out every Tuesday, especially if there is something that's going on that week. Otherwise, we will not send anything out. But I think there's pretty much been something going on every single week that we want to let you know that it's available for you to check out. And then next meeting is on May 2nd. Hope I got that right. And we will be featuring Professor Anna Williams of Macalester College. Ahmed, are you on to talk a little bit about what she's presenting? I thought I saw him on. Maybe not. I will have more details next time, and this is kind of my end of mine thing. And so I say thank you very much for being here tonight. Have a wonderful eclipse, but hold tight, because I believe I'm going to end my slideshow and let Ron Schmit share the screen so he can present an impromptu Presentation.
Trina,
Yeah.
Ahmed just put something in the chat. He cannot unmute for some reason.
No. I don't know. I don't have him locked out.
It worked.
Hang on, I gotta find him. Ask to unmute. No, I can't. I cannot unmute him either. I can ask to unmute. That's all right. Maybe he can put it in the group chat.
I got it to unmute.
Oh, okay. All right. So just, yeah, talk us about
Yeah.
next.
Yes. So actually, Professor Williams was the speaker we're going to have for today, but because of the eclipse and everything, we agreed to push it out for a month. And her talk is going to be about the galactic magnetic field study that she's been working on with radio telescopes and what she's been learning about the galactic magnetic field. So it's going to be a lot of fun talk. The other talk I want to highlight is going to be the June meeting. So like every eclipse, we're going to have a meeting to share eclipse images. And that's scheduled for the June meeting. So everybody send me your eclipse photos. Hopefully by the June meeting, you've got those processed and ready to share with the rest of the club. And you'll be prepared to also come out and talk about it in the June meeting. So thank you, Trina.
Yep. That also includes pictures of eclipse things that are experiments that you did, things on the ground, and the people, because we want to see their reactions too. So
yeah, sun pictures and experience pictures, nature, all are welcome.
Yep. All right. Turn it over to Ron to have his presentation for us.
Fantastic.
Ron, you may take it away.
All right, I'm going to chat about the magnetic field in the Milky Way galaxy. Oops. Did you say we're covering that next month? Okay.
No, it's okay.
I'll do something else.
Thank you.
So, hey, everybody.
That'd be great.
I heard from Trina when she popped in on, what is it called? Slack. That's
Slack,
it.
yes, the
She
Slack
said
thing.
that no presentation was included tonight. And I thought, well, that's kind of, we have people tune in, people that are part of the organization, maybe even new to the organization. They want to come and get some astronomy information. I'm like, okay, we could do that. Even if you are on the road, we can still fit that. So I'm going to talk to you about the Kepler mission tonight and the search for exoplanets. We're going to start with a little video that kind of reviews the details of Kepler through the words of the people who are putting it together.
We have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
Kepler mission is a huge step forward in answering a question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the habitable zone.
The habitable zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and ice covered, planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours, and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length, covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures. But the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a Sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
Kepler will be looking in a region of the sky that you'll see almost every night in the summertime.
The field of view is kind of nestled underneath the wing of Cygnus the Swan, between Cygnus and Lyra. Now, in that area of sky, there are something like 6.5 million stars. Why do we need so many?
Because of the way Kepler looks for planets, we have to have planetary systems that are lined up so that the planet actually passes between the star and Kepler telescope in its orbit.
The probability of that happening if you just throw stars randomly down in our galaxy is something like 1 to 10%. It's small. So of those 6.5 million scattered over that 100 square degrees, only maybe 200,000 are interesting to us.
We select the 170,000 or so that are most suitable to look at for planets with the Kepler telescope. Finally, we expect to end up with somewhere between a few hundred and a few thousand signals that are really planets around the stars that we're looking at.
Well, this is the first time that photometry, the measurement of the brightness of stars, will ever be done at this level of precision. And it will be done simultaneously on more than 100,000 stars continuously over a period of years.
We're somewhat like pioneers, very much like the explorers that were looking for new lands to settle. And that's how I see what we're doing. We're looking in this region of our galaxy for other habitable worlds.
I think people everywhere want to know whether with all the stars out there, do they have planets that are Earth-sized? Are Earths frequent or are they rare? And this gives us that answer. It's the next step in mankind's exploration of the galaxy.
There's two extreme answers that Kepler might give us. It might tell us that there's an Earth-like planet practically around every star we look at. Imagine the possibilities for life in the galaxy, or life in the universe.
If, on the other hand, we found out that Earth was very special and that the typical star, like the Sun, is not hosting planets like the Earth,
I think that would be a real surprise as well, and would really make us reconsider the special nature of Earth.
We are now finally at the point where our technology allows us to build a machine that can make the observations to scientifically answer this question.
How many stars like the Sun did develop planets around them like the Earth? I think that's such an important question to everyone and so interesting that we really have to do it, and it's a once-in-a-lifetime opportunity right now.
There you go. So a quick little overview of what to expect from the Kepler mission. And now we're going to take a look at a little bit more detailed look at what it hoped to find, what it did find, and then what are the next steps after that. So I love this slide from Epicurus. He wrote a long time ago, there are infinite worlds both like and unlike this world of ours. We must believe that in all worlds, there are living creatures and plants and other things we see in this world. And that was thousands of years ago that people had thoughts like that. As heretical as that may have been. And if you look, there's lots of places that we can look. I mean, with this shot from the Hubble Space Telescope, the Ultra Deep Field, tens of thousands of galaxies in this view. Every one of those dots, whirlpool of a couple 100 billion suns. So it's a rich opportunity. Of course, we are going to start in our own galaxy, something a little bit more reasonable, and we first have to consider where we're at. And there we are, about 2/3 of the way from the middle. We're out in the 494-694 loop. We're out beyond the 494-694 loop in our galaxy. So we're not in the sticks, but we can see them from here. When we consider looking for planets around stars, we have to consider how long a star is going to last. And if we look at ours as an example, we start with its birth from a protostellar cloud. 4.8 billion years later, we are here at now, and we have the fully developed system. Really nothing else developing in our solar system. After the late bombardment period, a lot of stuff cleared up, a lot of stuff settled down into orbits. And for about 2 billion years, it's been what we see today. And not a whole lot of things have changed. Of course, 5 billion years from now, that's going to get a little sticky because our sun is destined to use up its fuel of hydrogen, converting it into helium, and then fusing heavier elements. And when it does, it's going to be a larger reaction, and that's going to create a giant star out of our little bitty sun. It'll grow in size. The surface will stretch out past the first 4 planets, and yes, we're on number 3. So the Earth does have an expiration date. After that, once the stellar furnace gets up towards iron, iron requires more energy to fuse than it releases. And so the star goes into debt. And that doesn't last very long. Soon the inside of the star goes out. The pressure holding out that surface is no longer there. And so the star begins to collapse. It collapses, a pressure wave builds up on the inside, and it'll slough the outer lining of our sun off into space. Now, a lot of people think our sun's going to explode. It's just too small to explode. It'll convert its essence into a planetary nebula with a hot white dwarf right there in the center, destined to burn for about another 10 billion years before it just eventually runs out of energy. And so the ultimate fate of our sun will be a Earth-sized chunk of charcoal. And who knows what the outer planets will have done by that time, but I imagine the solar system will be all used up. But don't worry, kids. We've got plenty of time to figure out what to do. I'm sure we'll be just fine. So its life cycle is mainly determined by its mass. Massive stars don't last very long. They burn up their energy fast and they die young. Like they burn out like rock stars. Smaller stars last for much longer. They burn their energy very slowly. So we are somewhere in the middle with our yellow dwarf star. Taking a look at our solar system, if we want to find life on a potential exoplanet, we do have to consider the habitable zone of that star. So here we have our terrestrial planets, our hard, rocky, crusty ones near the sun. We've got our gas giants out beyond that. And then we have our trans-Neptunian objects, Pluto, Eris, Haumea, Makemake, all of the dwarf planets you've heard about in the news are out in that end of things. The habitable zone is a spot in our solar system where water can exist in a liquid state. So it's not so close to the sun that liquid water would boil off. It's not so far that it would freeze on the surface. Because as far as we know, all life requires liquid water. Now, if you're a Star Trek fan, you're like, oh, there's all sorts of possibilities. What if it uses silicone? What if it uses germanium or something? You know, yes. Life could surprise us with the chemicals it uses. Life from another star system could certainly do that. But how would we even recognize it then? We got to start with what we know. And what we know is that all life requires liquid water. The habitable zone of our star, of our sun, goes from Venus out to Mars. And both of those are included, by the way. Venus is not habitable because of its horrible, horrible atmosphere. But it is far enough away from the sun that it could have liquid water on the surface had it not turned into such a horrible hot mess. And Mars is within the habitable zone of our sun. But had it not lost its atmosphere to the ravages of the sun, it would still have that ocean-covered body that probably looked a lot like Earth about 3.5 billion years ago. That entire northern hemisphere was covered with water. Even in this picture, you can see Valles Marineris, that giant canyon cut from water falling from the Tarsus Ridge and dumping out into Utopia Planitia and the northern sea that once covered Mars. Now, another thing we have to consider is that planets that are 10 times the mass of Earth will hold on to their hydrogen and helium and end up becoming a gas giant like Uranus or Neptune. So they can't be too big, and they can't be too small. Something that's less than half the size of Earth's mass can't hold on to a life-sustaining atmosphere. So you've got to find that balance in between. Now, again, might we be surprised by something? Sure. But again, we have to go back to what we know. The mission itself is named after Johannes Kepler, a German mathematician and astronomer from 1571 to 1630. He was around after Copernicus released his paper, and his boss at the time, Tycho Brahe, wanted him to do some math and prove this upstart Copernicus wrong. Well, he worked at it and worked at it and worked at it. And after 2 years, he finally came up with a solution. Interesting story there. If you can find something about Kepler and read up on him, he had to throw away kind of everything that he knew. He had to throw away all convention and everything that everyone else knew. Because even Copernicus's system, although he put the sun at the center, which was right, he couldn't get the math to work for the orbits. And you can see why he couldn't. Because just like everybody else, Copernicus was certain that the planets orbited in circles. Perfect circles, mind you, because in the heavens, everything must be perfect. And that confounded Kepler. He could not get the math to work. And you don't see it here, but if you'll remember the earlier models of our solar system, the use of epicycles tried to explain why retrograde would happen with the planets as they moved around the Earth in their orbits. And those epicycles were horrible mathematical constructs. And even they didn't work. Even Kepler believed in the epicycles. And when Copernicus put out his system, he still had epicycles, even though he put the sun at the center. It wasn't until Kepler realized that they weren't circles, they were ellipses. And that's when everything started to fall into place. With that, he developed his 3 laws. The first one is that the planets orbit the sun in elliptical orbits, with the sun at one focus. His second law was the equal areas in equal time, meaning the line connecting a planet to the sun sweeps out an equal area in an equal amount of time. Although this seems like a longer part of the orbit, the area is the same since it's closer to the sun. Although this seems a shorter orbit, it's farther away. So these areas are the same, and they sweep out the same amount of time. Finally, his third law was that the time required for a planet to orbit the star, called its period, is proportional to the long axis of the ellipse raised to the 3/2 power. Once he surrendered to the idea of ellipses, and it wasn't a pretty battle, everything came into place, and his math all worked. And since then, we haven't looked back. And now, as we look out into space to try to find other planets, about 330 planets were known to orbit other stars before the Kepler mission started. But all of these, as you can see on the right-hand side, were very large planets and very close to the sun because they were found using the radial velocity method. Now, about a dozen had been found by a transit method, but the transit method is much harder, as you're going to see. So, of the 330, almost all of them were gas giants. And most of them had very short orbital periods, or what they would call roasters or hot Jupiters, and none of them were considered habitable. Here you can see the relative mass of Gliese 581 compared to the Earth, and an orbital period of just 13 days. So the mass of Jupiter swinging around a star in just 13 days. I mean, Mercury takes 3 months to go all the way around the sun. So here's the radial method. The planet is a large mass, and it's close enough to the star that if you look at the gravitational pull between them, the center of gravity is actually not inside the star. The center is off in between the two. And what that does is as the planet goes around, it actually drags the star around with it. So the star is going towards you and away from you, and towards you and away from you. And you can detect that Doppler shift. You can detect that motion through a Doppler shift in the spectrum. Going blue when it comes towards you, red when it's moving away. And that's how they were able to use the radial velocity method. So again, they can't even see this planet. They're not even looking for it. They're just looking for this wobble in the star and using the gravitational math to explain how big that star might be and how far away it might be. Again, using Kepler's laws. So to find Earth-sized planets, that's what Kepler was developed to do. So we have a transit coming up on Monday. The moon will transit the disk of the sun in what we call a total solar eclipse. This is also a type of eclipse. If a planet were to pass in front of the star, as they said in the video, the light from the star would dim slightly. Now, what are the odds that the planets would line up just perfectly? So from Earth, we see the light dim, we see the planets passing in front of the disk. Well, it's only about 1%. But if you're looking at 150,000 stars at one time, that's still 1,000 candidates. So that gives you quite a bit to choose from. And although you would think that those odds aren't very good, again, by looking at a number of stars, we're able to find candidates. So in order to detect what an Earth-sized planet would do, we have to go out in space. See, Jupiter would block about 1% of the sun's disk, okay, as it went across. Earth would block only 0.008% of the sun disk. So the amount of drop in the light would be minuscule compared to something like Jupiter. So small that we lose that signal in the noise through the atmosphere. So again, by observing more than 150,000 stars, Jupiter has got a statistically significant number of systems it could choose from. And in that, we would have to figure out which ones are within the habitable zone as well. So the orbital period provides the distance from the star, and that tells us the temperature. The size of the planet, its mass, would give us an indication of its surface gravity. And then follow-up observations by future telescopes could reveal things like atmosphere and composition, things that we've done now with the James Webb Telescope. Transit spectroscopy, the word is. As the planet moves in front of the star, we actually see light from the star passing through the planet's atmosphere. Taking a look at that spectrum, we can find out what is in that atmosphere, and that's produced some exciting results. So here you can see the Kepler, James Webb, all excited. The Kepler spacecraft, you can see the telescope here, the solar array on the outside. Here's the radiator, and then inside the spacecraft bus here includes the pointing devices, the star trackers, thrusters, and a radio dish to transmit the data back to the Earth. There you see on the inside, Kepler is a big Schmit camera. So it's got a corrector plate, just like a Schmidt-Cassegrain telescope does. It has its 1.4 meter mirror in the back. And instead of popping it up to the secondary and then back out the telescope for the eyepiece, like one of our Schmidt-Cassegrains, like some of our telescopes out at Eagle Lake, it has a camera here instead. And as you saw in that picture, that camera has got some really big CCDs. So here's the actual telescope covered with a metal foil to keep it safe from radiation. There you can see the sunshade all tied up, boxed up, ready for flight. And it was launched from a Delta II rocket, March 7th, 2009. Probe is up here underneath that fairing, being launched from the Cape Canaveral Space Force Station. As I said in the video, it moved into an Earth-following orbit. So right here, this little blue dot is Earth on March 5th. Once it launched, 1 year later, the Earth is back to this spot on March 5th, but now Kepler is here. Another orbit around the sun, and now it's here. And 3 years later, it's here. And then 4 years later, it's here. So it continued to slide behind the Earth in its orbit. A heliocentric orbit centered on the sun, but flying a little slower than the Earth itself. And as you can see, Kepler had to face the solar panels toward the sun all the time. So it would roll to a position where it was facing the solar panels, but once it got 90 degrees in its orbit, it would have to roll them again. So they were pointed back to the sun. So they would do this roll maneuver at each solstice and equinox, trying to maximize the amount of energy they could get from the solar panels and provide thermal stability to the telescope, with the radiator on the other side dumping out extra heat.
Ron?
Yeah.
Why are they delaying it by a year? Why does it keep wanting to keep fall behind? What's the point of that?
I don't know.
Okay.
Just what they did.
Okay.
So the primary goal is to use transit photometry to detect Earth-like planets in the orbits around these stars. With 150,000 stars to stare at, it took up 100 square degrees of the sky. It looked like this. You saw the Hubble field he mentioned in the video. And there you see where it was in the sky, right here at the top of the summer triangle. Now, on purpose, they lifted a little bit above the Milky Way because they wanted to cut down on the number of stars they had to whittle through. And this would be a region that would give them plenty of results and yet not overwhelm and allow them to isolate and watch variations in the stars that they would find. Here you can see where that fits in the sky. There's our Milky Way galaxy. Here's the center of it right here. Here's the outside edge that we're looking at right now. This is our neighborhood. Rich in stars, but not too many giant stars that would mess up observations. And in the northern hemisphere, so we could follow up with ground-based observing with the telescopes we have. So we are on the inside of the Orion spur of the Perseus arm of our galaxy. We are headed in this direction. And so that's the direction that they pointed the Kepler in, not into the galactic disk, but a little bit above it to improve its view. So we've seen transits before. Transit of Venus in 2006, transit of Mercury in 2006, transit of Venus in 2012, 2017. We've seen these before, passing in front of the sun and blocking the light. Using Kepler's third law, we were going to be able to figure out not just the distance, but also the mass of those stars. So taking a look at how that fits in our solar system. Here's the Earth, Venus, and Mercury. Well, Earth goes around in 1 year, or 365 days. We can take time equal to that and solve for R using Kepler's law. And that gives us an R of 1 astronomical unit, which is 149,600,000 kilometers. So we could do the same with Venus and the same with Mercury as well. Using Kepler's law, we can figure out to show how that works in our solar system. So again, about 1% of all orbits will allow a transit to be visible. And of those, some of them will be Jupiter's. Jupiter will drop about 1% of the star's light and give you a nice big dip like this. Something like the Earth, much, much less. In fact, if you notice the scale here, this drops to about minus 8,000 parts per million in the change of flux. This drops just 100. And you can see all the noise in this signal. And this is from space. From the ground, there's so much noise coming through our atmosphere that they cannot make a reliable determination. So that's why Kepler was put into space. So this is data as of 2015. So I know this is a little old. The numbers are now up to about 6,000 candidate planets that they've found. But 20 years ago, most of these were the big Jupiters that had very short orbital periods, as you saw in that early graphic. These were found with the radial method. But now with Kepler, they have found a lot more bodies that are Earth size and Neptune size. Some that are very close to the star, but a lot of them that are much farther out, much closer to the kinds of environment that the Earth experiences. So taking a quick look at the distribution here, we had about 674 Earth size, which is less than 1.25 times the radius of the Earth. About 1,076 super Earths, which are anywhere between 125 to 200% the radius of the Earth. 1,457 Neptune size, 229 Jupiter size, and 102 super Jupiters. So those are the results they have found. Here's an example of one. This is WASP-47, a bright G-class star. It found a super Earth with a period of 0.8 days, a hot Jupiter with a period of 4 days, and a Neptune-sized body with a period of 9 days. So that amount of dip will tell us how big the planet is. The more light it blocks, the greater this dip. Of course, for the Jupiter-sized body, it dipped a lot. And this Neptune one, this looks like it's less of a dip than this, but if you notice the scale, this goes all the way down to 0.9990. This is only 0.99997. 0.9997, yes. So although the graph makes it look like a bigger dip, this is actually a smaller dip because of the change in scale. And this is what you would find. Staring at a star for years at a time, you would see a dip, and then another dip, and then another dip, and a 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 dip. And when you start to see a pattern that they repeat, you then have a candidate. Now, the B planet took a dip like this. The C planet took a dip like this. And the D took a dip like this. Now, these are all at the same scale. So which one is the biggest? Well, it would be B, then C, and then D. Now, the amount of time that it's dipped indicates the transit, how long it took to travel across the face of the star. If it was a short amount of time, in this case, it was only 0.8 days. A longer period of time, 4 days. An even longer period of time, 9 days. Which means that this body would be closer to the sun than this body, which would be closer to the sun than this body. So the farther out it is, the longer it's going to take to transit in front of the star. So going back to our dips and dips and dips, we can recognize a repeating pattern, and that's for planet B. We can recognize a repeating pattern for C, and we can recognize D. So B with the shortest period, then C, and then D with the longest. That makes D the farthest planet. Now, when we first started to look at this, we had to also consider habitable zone. Here is our solar system seen with 3 different suns. Our sun with a habitable zone that goes from just outside of Venus out to Mars. If our star were hotter, notice the habitable zone would go out farther because the inner portion would be way too hot. So in this case, with a hotter star, only Mars would be in the habitable zone. Mercury, Venus, and Earth would be too hot. And if our sun were colder or cooler, then we would end up with a smaller habitable zone. And in that the case, Mercury would still be too hot, but Venus would be in the habitable zone. Earth and Mars were not. And I see the chatter that the theory is about the loss of the Martian atmosphere is due to the collapse of the magnetic field. So Mars is a third the size of the Earth and twice as far from the sun. It cooled off on the inside, and when it did, the magnetic field went away, because in order to have a magnetic field, you have to have spinning iron on the inside. And once it cooled off, that spinning stopped. No spinning, no magnetic field, and the sun ravaged the atmosphere of Mars and tore it off. We actually have the MAVEN probe still in orbit around Mars, and it has measured the speed at which the sun is tearing molecules off of Mars, and it's much faster than we imagined, even to this day. All right, so here's some examples. Let's take a look and find out what's in the habitable zone and what's not. Sort of a galactic Goldilocks. So here's Kepler 22. As the Kepler mission would identify new candidate stars, it would number them. So this is the 22nd star that was numbered from the Kepler system, from the Kepler program. That's compared to our solar system right here. Now, let me add here too, this planet doesn't look like this. We do not know what it looks like. Our telescopes are not yet strong enough to image exoplanets. What we do know is, because of the transit, its relative size and its relative distance from the star. Any imagery you see is artistic license. Figuring out, oh, well, okay, that's probably going to be twice the size of the Earth, so you can make a disk, and then what color are you going to make it? Well, let's make it look like Camino or Mustafar or whatever. So going back to Kepler 22, there's our sun, the Kepler 22 star, and notice that our solar system, the habitable zone, goes out a little farther, meaning that this star is slightly colder. But Kepler 22b is within the habitable zone, and it has a relative size of this.
Is
Comparing
that
Kepler
with the giant water?
All right, go ahead.
Is that the one they're thinking is the giant water planet?
Yep.
Thank you.
Mm-hmm. All right, so Kepler 62, you can see the star is much smaller. Its habitable zone is much smaller than our solar systems. It has 5 planets in orbit and 2 of them within the habitable zone. Now, again, this one would be the closest. They made it look like Mustafar, like a super hot Earth that would be cooking away close to its star compared to our lovely solar system. Here's Kepler 69. You can see that its star is a little bit colder than ours because its habitable zone is smaller, and it has 2 planets around it that we've detected, 69b and 69c. And 69c is the one that's in the habitable zone. Here's Kepler 47. Again, a star that's much cooler because its habitable zone is smaller. They found 2 planets in orbit around Kepler 47, B and C, and you can see that only C is in the habitable zone. But notice the orbit. Do you see how it's eccentric? If you look really closely, you'll see that there is a companion star there. This is a solar system with a binary pair. So that binary pair sweeping around creates that eccentric ellipse where the planets in orbit around it. Here's Kepler 186, a much cooler star with a habitable zone that fits inside of our habitable zone, with little 186F in the habitable zone of that star. And then we have Kepler 452, a little hotter than our sun, with a larger habitable zone, or a habitable zone that hangs further out, I should say. And there you can see Kepler 452b orbiting in the habitable zone. And this is TRAPPIST-1. This kind of kills me because it has 7 planets, 3 of them in the habitable zone, 1 that's too cold, 3 that are too hot. But look at the relative scale here of those bodies. They're all close to the size of the Earth. But when we look at the system as a total, this whole system fits right here. On the top, this is enlarged by 25 times. The entire system of 7 planets would fit way inside the orbit of Mercury. So, of course, the star is much, much cooler than our sun. And these planets are so close. You know, in Star Wars, when they like look up from a planet and you see another planet right there as big and bright as a moon, there you go. That would be the TRAPPIST-1 system. Just like standing on Hosnian Prime and you look up and you see the other 2 and you're like, oh my goodness, planets right there in our sky. That's how close the planets of the TRAPPIST-1 system are. Now, when we consider habitable zone, we have to include the habitable zone of the Milky Way. Within this region, there's much too much radiation from the galactic core, with all this stuff spinning around at a high velocity, putting out all sorts of horrible X-rays and gamma rays. And then when we get out to the edge, it's metal poor with not a whole lot of star birth going on. So the heavier metals that we need to encourage an Earth-like planet form within this zone of our galaxy. So our galaxy has a habitable zone, and our solar system has a habitable zone. And that's why the Kepler field is looking within that habitable zone for its search area. Now, as I mentioned earlier, if we go with a planet that's too big, pretty soon as we get beyond 2 Earth-planet radiuses, it starts to get to be so large, there's a good chance it's going to hang on to its hydrogen and helium envelope. And then we're not going to have a hard, rocky, crusty planet with a surface that things can walk around on. It's going to be a gas giant like Neptune or Uranus. So we're really focused in on Earth size, habitable zone distance, a star like our sun. So if we go with what we know, there's a better chance that we're going to recognize life if we find it. So here's a G-class star like our sun, K-class star, some of the Kepler planets that have been found, and their size relative to Earth. This is all to the same scale here. and then M-class stars and the Kepler candidates it's found. So of all of the planets found, about 220 of them are similar in size to Earth and within the habitable zone. Again, the colors that you see here, completely made up. Don't get hung up on that, but it just gives you an idea of how big they are and how far away they are. 11 light years, 12 light years. Here's the one around Proxima Centauri b, 4.2 light years away, the closest of the exoplanets. Sadly, the closest is still 114,000 years away on board a Orion spacecraft. So we got to figure out some way to go faster. As we got to the end of the Kepler's primary mission, they tried to find a way to sneak out a little bit more life. What they did is they were running out of fuel to maneuver. So instead, they started to use sunlight to help with the fine pointing. And this is some smart thinking. See, in order to station keep and hold at that one spot and stare at those 150,000 stars, it had to use thrusters to hold it in place. But once the fuel was all used up, they used the gyros and the solar panels to help point the telescope so it could orient the solar panels where they could get not just maximum power, but a stable position. Now, what they did is they had to sacrifice pointing at one spot in space. So they were able to use sun pressure to hold the telescope in space and make it stable, but then they had to move and look at different areas. So they looked at field 1, and then when they rotated to prevent sunlight from coming into the telescope, they had to move to field 2, and then field 3 and 4, and so on and so on. The way that looked was, instead of the original Hubble field that they had to compromise and take something along the ecliptic. So yes, that was going to give it a much more crowded field, but it was better than the mission ending. So they were going to make the best of what they could do, and they called that campaign the K2. So kind of a second lease on life for the Kepler mission. So they ended up looking at some very interesting places, like around the Pleiades and the Hyades, in Upper Scorpius, around the Scorpio region. What have we got? M3 up here? Is that M3 in there? There's some nebula regions. There's a lot of starbirth there. So finally out of fuel on October 30th, 2018, the Kepler mission ended. And what's next? TESS was right there to take over. TESS stands for the Transiting Exoplanet Survey Satellite, and they were going to do exoplanets a whole other way. Let's take a look at a short video that's going to tell us how TESS does its job differently than Kepler.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, TESS will find thousands of new planets orbiting nearby stars. During its 2-year survey, TESS will watch a wide variety of stars, looking for signs of planets ranging from Earth-size to larger than Jupiter. Each of TESS's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a long strip of the sky called an observation sector. TESS will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year, and then begin scanning the north. TESS will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed. making TESS the first exoplanet mission to survey nearly the entire sky. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the two missions to work together to first find and then carefully study exoplanets, expanding our understanding of worlds beyond our own.
Yes, Mark. Oh, okay.
The TRAPPIST one, that was a red dwarf, right?
Yep.
Thank you.
So TESS was launched April 18th, 2018. And as the video said, it's scanning a much larger part of the sky, including the poles. The poles get overlap for both the north and southern hemisphere. So they get extra information. And those are the K2 fields that we talked about. This was the original Kepler field. And then the secondary mission, getting what they could, where they could, along the ecliptic. And boy, have they found lots of planets. None of them look like this, as far as we know. We cannot image any of them, but go ahead and use your imagination. If you look in Stellarium, Stellarium actually has a setting for you where you can turn on the Kepler field and all of the exoplanets. And of course, the Kepler field is just rich with exoplanets. That's where most of the 6,000 are located. And the nice thing about TESS is as it finds them, those polar regions are spots that the James Webb can go to. You know, that James Webb can't point towards the sun, around the sun at all. It's got to keep that sun shield there. But directly north and directly south of the ecliptic, it certainly can do that. So TESS can hook them and James Webb can clean them and fry them. All right, do you have any questions I might be able to answer for you?
How long do you think they TESS is going to keep working? What's the expected life?
Primary mission 7 years long. So as they find results, they can reevaluate how long they want it to go. There's the mitigating fuel, and it does have electrical power for the gyros. And the gyros are a lot better. Gyros from back in the space shuttle days weren't doing very well because they found a problem with radiation on the spacecraft would decay the bearings, and then the gyros would stop working properly. One of the reasons that Hubble lost almost all of its gyros. They replaced them with ceramic bearings and have had a much better response, and TESS has the ceramic bearings. So things are working much better for it.
Excellent. Okay.
Ron?
Yeah, Mark.
I grew up watching the Carl Sagan Cosmos series, and I remember very well that one formula that someone worked up about the number of possible planets that could have life and so forth and all that.
Mm-hmm.
And
that's the Drake equation.
Yes, thank you.
Yep.
And I'm wondering, has anyone really reassessed that formula with some of the planets they've now find the small number they've had in a small space, but has so many different planets? Now, has anyone really looked at that formula and done some number crunching of that, please?
You know, I don't know if they've used any of the Kepler candidates in the Drake equation, but I know the Drake equation has been revised several times with some major considerations for what they call the Great Filter. And I don't know, this late in the evening, if I want to bring it up, it might wreck your sleep a little, because people have stopped at their consoles of SETI and the VLA and all these massive listening devices, and they've noticed that in our advanced period of our instrumentation, we still haven't found anything. And that's kind of weirding people out. Fermi's paradox is if there's so many stars out there, there should be lots of people. If there are lots of people, beings, what have you, we should have heard from them. And yet it's been completely quiet. So now you see uh, people talking to, like Brian Cox the other day was presenting the idea that, we very well may be the only sentient life in our galaxy. When first you look at 200 billion stars, of course there's got to be life out there, otherwise it'd be a great waste of space. And yet in our neighborhood, we still haven't heard anything. There was the WOW signal that SETI had, but that didn't repeat, and there was no other data for that. But there's never been one that's like, boy, that's really, well, I shouldn't say never. There have been gamma ray bursters and large bursts from quasars that eventually were identified as, oh yeah, okay, well that's a radio emission from something we didn't know existed, but now we have an understanding of it, and we've got a much better idea what that was. But we still haven't received any significant signals of, non-natural origin. And that's getting people to consider maybe one of the components in the Drake equation is civilizations don't last that long. And Sagan presents that very profoundly in his Demon Haunted World. And in the Pale Blue Dot, he talks about, the same time that we have figured out our place in the cosmos is simultaneously the time that we figured out how to destroy that place. With the development of nuclear weapons, we could sanitize the planet. And it's interesting that at the time that our technology has developed enough that we have an understanding that, hey, this is a very unique outpost here in the vastness of the Milky Way, yet we have the ability to completely make it disappear. That's incredible. And that's a very profound thought. So if that has repeated in other civilizations throughout our galaxy, maybe that's why we're not hearing anybody. Maybe there is a point where the technology becomes so overwhelming that it wipes out whatever life forms are there. And again, it gets pretty dark, especially when people start talking about AI and the things of our technology now that, have the ability to grow beyond us. Then maybe it makes sense that we're not hearing any other voices out there.
Ron?
Yeah. But by the way, sleep well, kids. Sorry. Yeah, Mark.
I'm a veteran of the United States Navy.
Thank you for your service, sir.
Well, I served during the Reagan fiasco.
The fiasco being
Ronald
years
Reagan.
of prosperity?
No.
Keep going, Mark. Keep going.
Any rate, I'm looking at where we're at now, behavior, Vladimir Putrid and his empire building, and not to mention so many other aspects. And I'm
okay, stay focused.
Yeah, and I've been asking a question to another veteran. Are we ready for nuclear power? And the answer I keep coming back to is hell no.
Wait, you mean like the generation of electricity through nuclear energy?
Nuclear power in general. Because you can't get nuclear power without the possibility of nuclear weapons, too, sadly. Not to mention nuclear other stuff. So there's, unfortunately, how mature of a species are we is a question. And going back to that Drake equation, there is a question of maturity of a species out there.
Sure.
And little fun for everyone out there. I should make this to everyone. There was a website. I don't know how many people have ever seen it. Basically, someone came up with this little website piece they did. If the moon was one little teeny tiny little pixel, and scale that for the whole solar system, how big of display would that be? I just posted it out for the chat. And I've seen it a couple of times, and it basically is mind-boggling how bloody big just our solar system is.
Yeah.
And then considering how big our galaxy is, and then how many other galaxies are out there.
Mm-hmm.
And after Hubble's deep field, viewing and how much more they've seen. The question is, how bloody big is it out there, and what's the other chances of life or such out there?
Right. Right. Well, I showed the Hubble Deep Field early on, and that's 10,000 galaxies in a spot in space that you could cover with a pencil tip at arm's length. And they didn't just get lucky with that. You move the pencil over a little bit to the left, there's another 10,000. You move it over to the right, there's another 10,000. So there are about 2 trillion galaxies out there in a space that now is about 96 billion light years across. So yeah, the universe is massive. And I see science fiction from time to time taking great creative license and being apparently bored with the 200 billion stars we have in our Milky Way and having to go to other galaxies. Well, to get to another galaxy is a ridiculous proposition. And I don't care if you've got, hyperspace capable whales or whatever you want to come up with, Star Wars, but it's a ridiculous amount of distance. So if we happen to see any traffic out there between the stars, it's got to be from a severely advanced civilization. I don't know if you caught anything. There's a company down in Houston, Texas, that is working with the idea of the warp drive, the cubiary drive, and the idea of warping the space around instead of traveling through space, but warping the space a la Star Trek. And although I got to visit their lab, and although they were coming up with some great experiments, it's still just an idea that someone came up with, and no one's got the physics to explain that or to tie that off and say, oh, well, here's the route we take. Now, of course, a lot of things started and ended that way, but there is someone at least doing research in that idea of, how can we go faster to some of these places? Because like I said, just Proxima Centauri alone could take 114,000 years, 250,000 years just to get out to Sirius. And that's the 5th closest star to our sun, and then once we get out there, well, granted, Centaurus, Proxima has Proxima b, which is Earth-like and in the habitable zone. So maybe that is our best effort, but who's going to make a ship that can go fast enough to get out there? That would be the next great challenge.
I'm sure somebody out there will do it.
Well,
not in our lifetime.
I tell the kids, I tell them, we invented the internet for you, and you're welcome. Now do us the solid of, some transluminary type of transportation.
Exactly.
There you go. We're not asking much.
No.
Oh,
no.
that, and they're going to have to pay off the national debt, but biggest dine and dash in history. Yeah, exactly. Any other questions out there? I don't know if you guys have got the opportunity to see the information about the comet that's out there right now, but it is headed towards the sun. So it's going to disappear from our skies. So if you've not seen it yet, let me back up time a little bit here. I'm off in Stellarium, and you can see at, we get down to about 8 o'clock here. It's getting very close to the horizon. You can see Jupiter there. It's Comet 12P or Pons Brooks, and there have been some nice pictures online of it that you can go out and check out. And if you do want to try to see it in the sky, it's going to be diving towards the sun, and we are going to be out of luck pretty quickly. So there's a nice shot of it. It looks a lot like Comet Hyakutake.
Gorgeous.
One other thing to go out and take a look at, as Jerry would tell us, get out there and observe.
Exactly. Very much so. I didn't do that tonight, did I?
No, you didn't.
All right.
And I lamented I missed it. You could do it now.
All right, everybody. Get out there and observe.
There you
Have
go.
a great night.
All right.
Thank
Thanks,
you,
boss.
Ron. Everybody loved your presentation, at least the people online. Hopefully you can read those.
All right.
All right, everybody. Have a great night. Thank you for joining us.
Have a great Monday.